All right, let's dive into something really cool. We're going to explore this hidden symmetry in the world of numbers, a secret connection that links integers that, on the surface, have absolutely nothing to do with each other. It's wild. So let me ask you this. What if you could take two totally different numbers, completely unrelated, and somehow turn them into 3D shapes that are, in a way, geometric twins? Sounds a bit weird, right? But stick with me, because this strange question leads to a really fascinating discovery. Okay, so to even begin to unpack that, we've got to start with a really simple but super powerful idea. And it's this. Some numbers have this special relationship with their own mirror image. You know, the most famous example of this is a type of number called an emirp. And yeah, you guessed it, that's just the word prime spelled backwards. An emirp is basically a prime number that when you flip its digits around, you get another totally different prime number. Think about the number 17. It's a prime number, right? Now flip it, you get 71. And what do you know? 71 is also a prime. Boom! That means 17 and 71 are a pair of emirps. And this whole idea of reversibility, that's the first big clue to solving our puzzle. All right, now let's take this idea, this flipping of digits, and move it from the flat 2D world of numbers on a page into something 3D. We're literally going to go from numbers to shapes. Okay, so the main character in our story today is a special kind of number called a sphenic number. All a sphenic number is, really, is a positive number that you get by multiplying three different prime numbers together. Just think of them as these little structures built from three unique prime building blocks. Let's make this real with an example. Take the number 165. It's a sphenic number. And why? Because you can break it down into three distinct prime factors, 3, 5, and 11. Yep, those are our secret ingredients right there. Okay, and here's the leap. This is where we go into 3D. We can actually picture these numbers as a 3D rectangular block. They call it a sphenic brick. The length, the width, and the height of this brick are just those three prime factors. So for our number, 165, we get a brick that's 3 units by 5 units by 11 units. And the volume of that brick? Well, 3 times 5 times 11 is, you guessed it, 165 cubic units. Pretty neat, huh? So let's recap. We have numbers that can be flipped, and we have these sphenic numbers that we can turn into bricks. Now, what happens when we put these two ideas together? Well, that's where we uncover this really cool mathematical mystery. So here it is, the big question. What if we take a sphenic number, reverse its digits, and that new number also happens to be a sphenic number? And then, what if we build a brick for the original number and a brick for its reversed twin? Could those two totally different bricks with completely different dimensions actually have the exact same surface area? All right, let's test this out. Our first test case is the number 366. You might know that one. It's the number of days in a leap year. And it just so happens to be a sphenic number with the factors 2, 3, and 61. Okay, now let's flip it. We get 663. And guess what? This is also a sphenic number. But look at its factors. 3, 13, and 17. They're totally different from the first set. So do they match? We've got two different numbers, which give us two sphenic bricks with completely different dimensions. One is a 2 by 3 by 61 brick, and the other is a 3 by 13 by 17 brick. But, and this is the crazy part, when you actually calculate the surface area for both of them, they are identical. Both bricks have a surface area of exactly 622 square units. Wow, that is the hidden connection we were looking for. Now, I know what you're thinking. Now, I know what you're thinking, okay? That's a cool coincidence, maybe a 1 in a million shot. Well, it's actually even rarer than that. Let's dig in and see just how special these number pairs really are. So the researchers who found this, they scoured the first 3 million integers. And in that huge sea of numbers, how many pairs with this property did they find? Just 4. Only 4 pairs. These aren't just unusual, they are some seriously rare mathematical gems. And here they are, the whole list, all 4 of the known pairs. Just look at this.
Each row shows you one number, its unique prime factors, and then its reversed twin with a totally different set of prime factors. And yet, somehow, they share that one magical property, the exact same surface area. I mean, look at that last pair. We're talking numbers up in the 900,000s, and they share a surface area of over 190,000. That's just incredible.
So that leads to a natural question, right? Is this amazing property just a thing for 3D Spironic bricks? Or could this pattern maybe exist in other dimensions too? Well, let's try stepping down a dimension. What if we look at numbers made from just two prime factors? They're called semiprimes. Instead of 3D bricks, we can make 2D rectangles. And guess what? The same kind of thing happens. It turns out there are 13 pairs of these semi-prime rectangles under 1 million that share the exact same perimeter. So yeah, the pattern holds up. We could even get a little wild and go up to 4 dimensions, creating what are called hypercuboids from numbers with 4 different prime factors. Now, researchers have looked for this, but so far they haven't found any pairs that share a hypersurface area. But the key word there is yet. The search is still on. You know, this whole journey, from just flipping digits to building 3D bricks, it really shows us something profound. It shows that numbers can have these hidden geometric properties we'd never expect. And if a secret as specific and weird as this can exist, it really makes you wonder, doesn't it? What other amazing, beautiful symmetries are just waiting to be discovered, connecting numbers and shapes in ways we can't even imagine yet? The universe of numbers? Well, it definitely still has some secrets to tell.